Imagine you're boiling water for tea, and your friend walks in with a wild claim. If you want this to freeze faster, you should use the hot water, not the cold. You laugh it off, thinking that's ridiculous. Hot water freezing faster? What if I told you that your friend might actually be right? This bizarre phenomenon, known as the Mpemba Effect, isn't just a myth. It's a real scientific puzzle that has baffled experts for centuries. Here's the kicker. Nobody fully agrees on why it happens. Theories range from evaporation to molecular structures, but even today, the Mpemba Effect is surrounded by mystery. And here's the really weird part. This effect doesn't always happen. Sometimes cold water does freeze faster. So what's going on here? Is this just a quirky physics trick, or does it hint at something much deeper about the nature of water itself? Stick around, because by the end of this video, you'll not only understand the Mpemba Effect, but also why something as ordinary as water might hold the keys to some of the universe's biggest secrets. Water. It's everywhere, flowing from our taps, filling our oceans, even making up most of our bodies. It's so familiar that we hardly ever stop to think about it. But here's the thing. Water is weird. It defies expectations in ways that no other substance does. It expands when it freezes. It has an unusually high boiling point for its molecular size, and it can even climb up walls through capillary action. But perhaps the strangest property of all is the Mpemba Effect, the idea that hot water can freeze faster than cold water under certain conditions. This effect was named after Erasto Mpemba, a Tanzanian student who stumbled upon it by accident while making ice cream in the 1960s. Imagine being in his shoes, trying to explain to your science teacher that boiling water froze faster than cold water, only to be laughed at. But Mpemba stuck to his observations, and eventually, scientists began to take him seriously. Now, over 50 years later, researchers are still scratching their heads. Why would hot water freeze faster? Shouldn't it take longer for the hot water to cool down to freezing point? What about heat transfer, energy, and basic physics? These questions don't just challenge our understanding of water. They challenge the way we think about science itself. To understand the Mpemba Effect, we first need to confront a fundamental problem: intuition. Everything about this phenomenon seems to go against common sense. You'd think that cooling hot water would require more time because it starts at a higher temperature. And in most cases, you'd be right. But under specific conditions, this seemingly backward result happens. The challenge for scientists has been replicating the effect reliably in experiments. Sometimes it works, and sometimes it doesn't. Even the slightest changes in factors like the container, water impurities, or the surrounding environment can affect the results. So, is the Mpemba Effect just a fluke? Or is there something real and repeatable happening here? Several theories attempt to explain the Mpemba Effect, and each one adds a piece to the puzzle. One of the simplest explanations involves evaporation. When hot water is exposed to the air, it loses heat more quickly due to evaporation. This reduces the overall volume of water that needs to freeze. Less water means less time to freeze. But here's the twist. Evaporation alone doesn't account for every instance of the Mpemba Effect. Hot water creates stronger convection currents as it cools. These currents can distribute heat more evenly, speeding up the cooling process. Think of it like stirring a hot drink to make it cool faster. But again, this doesn't fully explain why hot water sometimes outpaces cold water. Here's where it gets even more interesting. Hot water can hold fewer dissolved gases than cold water. When these gases escape, the water's physical properties, like its density and freezing point, change slightly. Scientists are still debating. Water doesn't always freeze at exactly 0 degrees. Under certain conditions, it can cool below its freezing point without forming ice, a process known as supercooling. Hot water, as it cools rapidly, might avoid supercooling and freeze faster. And finally, there's the molecular level explanation. Water molecules form temporary hydrogen bonds, creating clusters that might behave differently depending on the water's initial temperature. Some researchers think these structural changes could play a role, but the evidence is still inconclusive. Here's where it all comes together. The Mpemba Effect isn't just a quirky physics fact. It's a reminder of how much we still don't know about the natural world. Even something as simple as water can defy our expectations and challenge our understanding. And that's the beauty of science. It keeps us asking questions. What's more, studying phenomena like the Mpemba effect could have practical applications. From designing better refrigeration systems to understanding how liquids behave in extreme conditions, this odd little quirk might lead to breakthroughs we can't even imagine yet. So, does hot water really freeze faster than cold water? The answer is, sometimes. The Mpemba effect is real, but it's not guaranteed. It depends on a complex interplay of factors: evaporation, convection, molecular structure, and more. But maybe the most important takeaway isn't the answer itself. It's the curiosity that drives us to keep searching. The Mpemba effect reminds us that science isn't just about knowing, it's about wondering, exploring, and embracing the mysteries that make our universe so endlessly fascinating.